Okay, so today I'm going to tell you about flat topological modules. And my main point is that while flat Banach modules are classical objects, very little is known about flatness in the more general setting of locally convex modules, and especially in the nonmetrizable setting. It turns out that even the definition of a flat topological module is not entirely obvious. So to begin with, let's recall some basic notions of Banach homological algebra, which was initiated by Alexei Pirkovskii in the early 1970s. And a bit later, excuse me, a question? No.
Okay. No question. Okay.
Okay. So so I'd like to recall some basic notions of Banach homological algebra, which was initiated by Alexei Pirkovskii at the beginning of the 1970s, and a bit later, but independently, by Reinhard Kühl and Jean-Louis Verdier, and again a bit later, but again independently, by Joseph Taylor. Okay, so suppose that we have Banach algebra A, Banach algebra, and the category of left Banach A modules will be denoted like this. And let's recall the following definition. If we have a short sequence of Banach A modules, then we say that the sequence is admissible if it is split exact in the category of Banach spaces. That is, if it has a contracting homotopy consisting of continuous linear operators. So geometrically, this means that X can be identified with a closed submodule of Y. Z can be identified with the quotient of Y modulo X. And moreover, X is complemented as a subspace of Y. And let's now recall the following definition due to Helemskii. We say that a left Banach A module P is projective if the following functor of morphisms, where P is in the first argument. So this functor is defined on the category of left Banach A modules, and it is exact in the sense that it takes admissible sequences of left Banach A modules to exact sequences of vector spaces. Similarly, you have a left Banach A module I, then I is called injective. If the functor of morphisms, where I is now in the second argument, so this is a contravariant functor on the category of left Banach A modules. So we say that I is injective if this functor is exact in the same sense, that is, it takes admissible sequences of modules to exact sequences of vector spaces. And finally, we say that a left Banach A module F is flat if the projective tensor product functor defined on the category of right Banach A modules is exact in the same sense. It takes admissible sequences of modules to exact sequences of vector spaces. Well, now an important property, an important fact about the category of Banach modules is that this category has enough projectives. This means that for each Banach A module X, there exists an admissible epimorphism. Well, I forgot to say what an admissible epimorphism is. Well, let's come back to the definition of an admissible sequence. So if we look at the sequence, so let's denote the first arrow by, say, I, and the second by P. So we say that P is an admissible epimorphism if it fits into a short admissible sequence of this form. So equivalently, this means that P is a retraction in the category of Banach spaces.
Алёш, прошу прощения, там немножко внизу не влезает. Может, пора перелистнуть страничку.
Да, сейчас, она не влезает просто по соображению масштаба, вот оно. Я перелистну, когда дело дойдет. Вот сейчас, может быть, просто какая-то задержка идет. Сейчас я...
А что?
Вот сейчас
у
видно,
меня
где...
все в порядке.
Вот сейчас видно, где дело все происходит. Вот короткая допустимая последовательность, вот она тут нарисована. Видно это?
Олег.
Ну как, сначала было видно, потом вернулось все назад.
Ну, я просто хотел показать на допустимую последовательность. Еще разок. Вот сейчас, вот я сейчас обвожу допустимую последовательность вот этой такой синей стрелочкой. Это видно?
Нет, это видно, но продолжение-то...
Ну, и так и задумано. Я просто сейчас напоминаю, что такое допустимый эпиморфизм. Хорошо, нормально. Я тогда продолжу, да?
Конечно.
Okay, so we say that P is an admissible epimorphism. P from Y to Z is an admissible epimorphism if it fits into a short admissible sequence of this form, or equivalently, if it is a co-retraction, if it is a retraction in the category of Banach spaces. And similarly, we say that I from X to Y is an admissible monomorphism. Again, if it fits into an admissible sequence of this form. So equivalently, this means that I is a co-retraction in the category of Banach spaces. Okay, let's now come back to this important fact about the category of Banach modules. So it has enough projective in the sense that for each Banach module X, there exists an admissible epimorphism from a projective Banach module P onto X. And also it is known that this category has enough injectives. Which means that for each Banach A module X, there exists an admissible monomorphism from X into an injective Banach module I. This fact is very important because it actually enables us to do homological algebra in the category of Banach A modules and to define derived functors. Well, today, our main focus will be on flat modules. Flat modules are important for many reasons. In particular, they are important because they are related to amenability of Banach algebras. So let's recall that if X is a left Banach A module, then the dual space X star has a canonical structure of a right Banach A module, and the right A module structure on X star is given by the following formula. And similarly, if X is a right Banach A module, then X star becomes a left Banach A module. And so This implies that if X is a Banach A bimodule, then X star is also a Banach A bimodule. And let's now recall the following definition due to Barry Johnson. So by definition, the Banach algebra A is amenable if for each Banach A bimodule X, all continuous derivations from A to the dual bimodule X star are inner. Well, I write all derivations assuming that we consider only continuous derivations. Amenability of Banach algebras is probably one of the most important, popular, and well-studied Banach algebraic properties. And it has many applications in, for example, harmonic analysis, operator algebra theory, representation theory, and in some neighboring fields of mathematics. A useful relation between amenability and flatness was found by Helemskii and Chainberg in 1979. So they proved the following result. Our Banach algebra A is amenable if and only if its unitization A plus is a flat Banach A bimodule. Well, of course, I'm not going to prove it now, but nevertheless, I'd like to recall three basic ingredients of the proof. The first ingredient is often referred to as Johnsonslemma. This result states that if you have a short sequence of Banach spaces, then it is exact if and only if the dual sequence is exact. Actually, I'm not sure if Johnson was really the first to state this result, but this seems to be the standard name.
Да, первый раз действительно у него, но вообще не надо быть Джонсоном, великим Джонсоном для такого результата.
Ну, это да, больше похоже на Банаха, я бы сказал. Okay, so this is the first important ingredient of the proof. Second ingredient is a special case of the adjoint associativity. So if we have two Banach modules, X and Y, X is a right module and Y is a left module, then the dual of their tensor product is isomorphic to the space of morphisms from X to Y star. And the third important ingredient is a nice duality between flat and injective modules, namely a left Banach A module F is flat if and only if the dual module F star is injective in the category of right Banach A modules. Actually, this fact, this duality between flat and injective modules, follows from the first fact from Johnsonslemma and from the joint associativity. Okay, by the way, useful corollary of this result, namely, of the Helemskii and Schoenberg theorem, is that if A is an amenable Banach algebra, then each left Banach A module is flat. And by the way, it seems to be an open problem of whether the converse is true. So far we have no concrete counterexample, and we have no proof. Okay, so this was a short introduction devoted to Banach theory. So what we want to do is to extend the notion of flatness to the setting of locally convex topological modules. So first of all, let's specify the type of topological algebras we are going to consider. All our topological algebras will be algebras relative to the completed projective tensor product. By definition, this means that they are complete locally convex and with jointly continuous multiplication. So if we have such an algebra A, then the multiplication on A uniquely factorizes through the completed projective tensor product of A by itself, which explains the terminology. Well, unfortunately, the standard name for such algebras, which is shown here, an algebra relative to the completed projective tensor product, is rather easy to write on the blackboard, but it's quite difficult to pronounce. So if you don't mind, I'll call them just topological algebras in my talk. So when I say topological algebra, I mean a complete locally convex topological algebra with jointly continuous multiplication. Well, of course, there are many natural examples of such algebras. Of course, each Banach algebra is a topological algebra in this sense, but there are many other natural examples. For example, we can take the algebra of continuous functions on a topological space X, and if X is not very bad, then this is a topological algebra in our sense. So the only possible problem is with the completeness of the space. But for example, if X is a locally compact Hausdorff space, then C of X is complete, so it is a topological algebra in our sense. We can also consider, for example, the algebra of smooth functions on a smooth real manifold, the algebra of holomorphic functions on a complex manifold M, the Schwarz algebra on Rn, equipped with either the pointwise product or with the convolution product. Important examples of nonmetrizable topological algebras are the algebra of compactly supported distributions on a real Lie group G, and the algebra of analytic functionals on a complex Lie group, which is defined to be the dual of the algebra of holomorphic functions, equipped with the convolution product. And there are many other natural examples. So if we have a topological algebra A, I mean topological algebra in this sense, then it is natural to consider topological modules also relative to the completed projective tensor product. So by definition, a topological module over a topological algebra A is a complete locally convex space equipped with the structure of a left A module such that the action of A on this module is jointly continuous. So I'll not write this down because this is quite obvious. And at this point, I'd like to slightly change my notation. Namely, I'll denote by A mode the category of all left topological A modules. Okay. Now, if the algebra A has some special linear topological properties, then it seems reasonable to consider only those topological A modules whose underlying linear topological space has the same properties. So to achieve this, let's introduce some notation and some definitions. So the category of all complete locally convex spaces will be denoted like this. Category of complete locally convex spaces. And suppose that we have a full additive subcategory. It's great to see. A full additive subcategory. We say that C is admissible if it is stable under completed projective tensor products. So if E and F are objects of C, then their completed projective tensor product is also an object of C. And second, if it is stable under topological direct summands. If E is isomorphic, topologically isomorphic to the direct sum of two spaces E0 and E1, and E is an object of C, then the summands E0 and E1 are also objects of C. Well, most of the categories of complete locally convex spaces which are used in functional analysis are admissible. For example, we can take the category of Banach spaces, the category of Fréchet spaces, the whole category of complete locally convex spaces, or for example, the category of complete barreled DF spaces, which will be defined a bit later. So all of them are admissible. Okay, now suppose that A is a topological algebra whose underlying topological vector space is an object of C. So I abbreviate this in this way. So this means that the underlying space of A belongs to C. If A is such an algebra, then it seems reasonable to consider only those topological A modules whose underlying topological vector space belongs to C. And the category of such modules will be denoted like this. So again, this is a full additive subcategory in the category of all topological A modules. We can now easily define projective and injective objects in this category. Projective and injective modules. In our category A mode of C, of topological A modules, they are defined in exactly the same way as in the case of Banach modules. And this seems to be the only reasonable definition of projective and injective modules. Okay, at this point, it seems reasonable to define flat topological modules in exactly the same way. So we say that F, we left topological A module F in our category is flat if the projective tensor product functor takes admissible sequences of right topological modules to exact sequences of vector spaces. So this is exactly the definition of a flat topological A module from the book by Alexander Yakovlevich, Homology in Banach and Topological Algebras. However, what I'm going to do is to convince you that this definition is not very convenient in the nonmetrizable case. And because of this, I'll call such modules not just flat, but rather vectorially flat. The word vectorially reflects the fact that we consider here the tensor product functor as a functor with values in the category of vector spaces. Well, now coming back to projectivity, we still have the same useful fact, which was already mentioned in the Banach case, namely our category of topological A modules has enough projectives. But on the other hand, there are some bad properties of this category. Some bad properties of the category of topological modules, which exist only in the case where C is different from the category of Banach spaces. The first bad property is that, in general, we have no injectives. More exactly, this means that there are many natural topological algebras such that the only injective topological module over such an algebra is 0. For example, this is true if we take the algebra of holomorphic functions on the complex plane, or the algebra of smooth functions on the real line, but there are many other natural examples.
Yes, but your very known theorem concerns Fréchet algebras, as far as I remember.
No.
Or I'm wrong.
No, this is not essential. This is also, we can take the algebra of germs of holomorphic functions, for example, which is a DF algebra, and we have the same result. The metrizability here is not essential. And C is not necessarily the category of Fréchet spaces. We can take any, actually any admissible category which is bigger than the category of Banach spaces, and the result will be the same.
Thank you.
So this shows that the nice duality between flat and injective modules, which exists in the Banach setting, is no longer available in the context of topological modules. And moreover, we have another problem related to duality. In general, there is no notion of a dual module. We have no dual modules. This means that if X is a left topological A module, then X star, the dual space, well, we will always equip the dual space with this chunk topology, the topology of uniform convergence of unbounded sets. So it is still a right A module, but it is not a topological module in our sense. which means that the action of A on the dual module is not jointly continuous. Okay, let's now suppose, so far I suppose that C is different from the category of Banach spaces. Let's now suppose that C is also different from the category of Fréchet spaces. In this case, we have some more problems, some more bad properties. It turns out that Johnsonslemma fails in general. Also, in general, the joint associativity fails. So at this point, let's recall that all these results, I mean, the joint associativity, Johnsonslemma, and the duality between flat and injective modules, all of them play an essential role in the proof of Helemskii-Schoenberg's theorem, which relates amenability to flatness. And this shows that we face serious problems if we wish to extend Helemskii-Schoenberg's result to the non-normable case. Another problem related to flatness is that co-kernels are not surjective in our category. Maybe I'd like to explain this in a little bit more detail. So let's recall that you would have an arbitrary additive category A and a morphism F from X to Y in our category. Then the core kernel of F is a pair consisting of an object C and a morphism little c from Y to C, such that first the composition of C and F is 0, and second, this pair is universal in the sense that whenever we have another object Z and a morphism G, such that the composition of G and F is 0, there exists a unique morphism H which makes the diagram commute. And in this case, we use the following notation. The object C is the co-kernel of F, and the morphism little c is also the co-kernel, but here we use little c. Okay, so this is the general category theoretic definition. And here are concrete examples. For example, if we take the category of vector spaces, then in this case, C is just the quotient of Y modulo the range, the set theoretic range of F. And the same is true if we take the category of all, that is not necessarily Hausdorff, locally convex spaces. So this is big C, and little c is just the quotient map. If we take the category of normed spaces, or the category of Banach spaces, or the category of Fréchet spaces, or the category of Hausdorff locally convex spaces, then the situation is different. In this case, the co-kernel C is the quotient of Y modulo the closure of the set theoretic range of F. Yeah. And finally, if we take the category of all complete locally convex spaces, then the co-kernel is the completion of this quotient. So let's recall that in general, the quotient of a complete locally convex space modulo a closed subspace is not necessarily complete. So we have to take the completion. And in this case, little c, the co-kernel of f is not surjective. Well, this fact leads to serious difficulties when we try to prove something about flat topological modules. And to understand these difficulties better, let's look at some obstructions to flatness. Obstructions to flatness. So suppose that we have an admissible sequence. An admissible sequence of right topological modules. So in general, if we apply the tensor product functor by f, so we look at the following sequence. And in general, if we know nothing about f, then the sequence is not exact in the category of vector spaces. But why? Why is it not exact? Well, let's consider separately 3 different cases. First of all, let's look at the purely algebraic case. I mean that we assume that A is just an algebra without any topology. And of course, we have to replace here the projective tensor product by the usual algebraic tensor product. So why is the sequence not exact? Let's recall that in the algebraic case, the sequence is always exact here and here. In other words, the algebraic tensor product is right exact. So the only reason why the sequence is not exact is the possible non-injectivity of this arrow. So in some sense, the obstructions to the exactness of the sequence sit here in the first term of the sequence. So the obstructions are in the first term. Okay, now let's consider the case of Banach or Fréchet modules. In this case, the sequence is still exact here in the last term, because the completed projective tensor product of 2 surjections is again a surjection. So it is exact here, but in general, it is not exact here. We can only say that the range of this morphism, of this arrow, is dense in the kernel of this one. So it is algebraically exact, if and only if this morphism, this first arrow, is injective and has closed range, which is equivalent by the open mapping theorem that this arrow is topologically injective. So in some sense, we see that the obstructions to the exactness of the sequence sit in this module, in this space, and in this space. Obstructions are here and here. Well, let's now look at the general case of arbitrary topological modules. In the general case, this sequence is not exact here, is not exact here, and is not exact here. And we see that in some sense, the obstructions are everywhere. And this leads to serious problems when we try to prove something interesting about flat topological modules. So if we adopt the straightforward, that is the naive definition of a flat topological modules, so if we just generalize it directly, literally from the Banach case, we can imagine a hypothetical module F, which must be flat for some reasons, which behaves like a flat module, but which is not flat for the only stupid reason that this last arrow is not surjective. And what I'm going to do now is to give a concrete example of such a module. Okay, so now suppose that T is a Hausdorff locally compact topological space. And let S be a closed subset of T. We will need the following lemma.
Subspace.
Excuse me?
You said subset?
Closed subset. Well, yeah. Closed subset. T is a locally compact topological space.
Just subset. Okay.
And S is a closed subset.
Good.
First of all, it is well known that C of T, the algebra of continuous functions on T, is complete. This is standard. This is well known, and this is a standard exercise in topological vector spaces. Second, let's now look at C0 of T. So this is a Banach algebra, and let's consider the restriction map from C0 of T to C0 of S. This is well defined because S is closed. So the restriction of a C0 function on T is against C0 on S. This map is surjective. This is also an easy exercise. We can reduce everything to the compact, to the situation of compact spaces by using one-point compactifications. And in the case of compact spaces, this surjectivity follows from the Titze-Urysohn extension theorem. Okay, let's now replace C0 by C. So we consider the spaces of all continuous functions. What can I say about the restriction map? I claim that it has dense range. Well, this is also very easy. This can be easily deduced from the Stone-Weierstrass theorem. Another property is that this restriction map is an open map onto its range. This is not very hard, but this is at the same point, this is not as trivial as the previous results. Actually, this result was first observed by Ptak in 1953. And by using this lemma, we get the following corollary. Corollary 1, also due to Ptak. Actually, this was one of the first examples of an incomplete quotient of a complete space. So suppose that T is locally compact, but non-normal Hausdorff topological space. concrete examples of such spaces are quite exotic, but they can easily be found, for example, in the well-known book by Engelking or in the original paper by Ptak. Since it is no normal, we can always find a closed subset S of t, such that the restriction map from C of t to C of S is not surjective. Well, indeed, T is not normal, so there are two disjoint closed subsets in T which cannot be separated by open neighborhoods. And so they cannot be separated by a continuous function. So there is no continuous function on T, which is identically 1 on the first closed set and which is identically 0 on the second one. And so now we denote by S the union of these two sets, and we consider the function which is identically 1 here and identically 0 here. And this function cannot be extended to T. And so the restriction map is not surjective. Let's now denote by E the ideal in C of T, which consists of all functions vanishing at S. Then we see that both C of T and C of S are complete because they are locally compact and Hausdorff. So they are complete. C of S is topologically isomorphic to the completion of the quotient of C of T modulo I. This easily follows from statements 3 and 4 of our lemma. So the restriction map has the dense range and it is open onto its range. But at the same time, the quotient itself is not complete. It is not complete because if it were complete, then the restriction map would be surjective. But it is not surjective. Okay. And now we can use this example to construct the following objects. I claim that there exists a locally compact Hausdorff topological space omega and a topological module over the algebra C0 of omega, which is not vectorially flat.
Yeah.
Well, why is it strange? This is strange because, well, let's.
Amenability, yes.
Yes, let me remark that C0 of omega is amenable. And so all Banach modules, and in fact, this easily extends to Fréchet modules, all Banach and all Fréchet modules over this algebra over C0 of omega are flat. Or vectorially flat. For Banach and Fréchet modules, this is the same. Okay, how can we construct such omega? We just take the space S and the subset T as in corollary 1. So T is locally compact Hausdorff topological space, and S is a closed subset such that the restriction map is not surjective. And let omega be the complement T minus S. It is locally compact because an open subset of the Hausdorff locally compact space is also locally compact. So we denote by A the algebra C0 of omega, and we denote by B the algebra C of T. We have an HL map, an HL homomorphism iota from A to B, which is defined as extension by 0. So if you have a C0 function on omega, we can extend it trivially to the whole of T, and it's easy to see that the resulting function will be continuous, and the iota is a well-defined continuous homomorphism. The continuous homomorphism. So we see that B becomes an A module, a topological A module. So the action of A is determined by iota. And I claim that B is not vectorially flat. Well, to show that it is not vectorially flat, we have to construct a suitable short admissible sequence. And we just take the simplest short admissible sequence, which can be associated to any topological algebra, namely the following one. Let's try to tensor it by B. I claim that the following map is not surjective. So if we tensor the whole sequence by B, then the resulting sequence of vector spaces will be not exact in the right term. Well, why is it not surjective? Well, the first space here is canonically identified with B, and the second one is canonically identified with the completion of the quotient of B modulo A B. And this error becomes the quotient map. Well, this is why is it so? This follows from the next simple lemma, which can be proved in exactly the same way as in the Banach case. If we take a closed right ideal in the unitization of some topological algebra, take the completion, and then take the projective tensor product by an arbitrary left topological module X, and this is topologically isomorphic to the completion of the quotient of X modulo Ix. So when we apply this to our situation, we see that this tensor product is identified with the completion of this quotient. But we already know from lemma 1, from corollary 1, that this quotient is not complete. So to show that this map is not surjective, it suffices to show that our ideal I is equal to the closure of AB. That is just to the closure of the range of iota. And why is it so? Well, let's look at the following picture. So this is A. A is C0 of omega. So clearly, iota takes A to our ideal I. So let's recall that I consists of all functions which vanish at S. So I is an ideal in C of T. And to show that the range of iota is dense in I, we take any compact subset K of T. So we have here the restriction map of C of T onto C of K. And we introduce similar ideal IK in C of K, which consists of all functions on K, which vanish at the intersection of K with S. So we get the following diagram. And by the definition of the topology on I, the topology on I is just the projective topology generated by all arrows of this form for various compact subsets of T. To show that the range of I is dense in I, we have to show that the range of the composed map from here to IK is dense in IK. Well, but what is IK? IK is a closed ideal in C of K, and K is compact. So it's easy to see that IK can be canonically identified with C0 of omega intersected with S. And this map becomes just the restriction map. And now we look at our lemma again. I mean, here, the restriction map from C0 of T to C0 of S is always surjective. So this arrow is surjective because omega intersected with S is a relatively closed subset of omega. So it is surjective, and moreover, it has dense range. And this implies that iota has dense range. And this completes the proof. So we see that B over A is not vectorially flat. Of course, this looks like a nonsense because A is amenable. So the fact that there exists a non-flat, well, non-vectorially flat module over C0 of omega suggests that perhaps our initial definition of a flat module has to be modified.
Yeah.
And to give a modified definition, let's recall some category theory. Let's recall some basic facts on strictly exact sequences. Well, suppose that we have an additive category A. And we have the following definition. A short sequence in our category. So let it be F, and this is G. And a short sequence in our category is strictly exact. Strictly exact if F is the kernel of G and G is the co-kernel of F.
Yeah.
Well, let's now look at some concrete examples. Example 1. If our category is abelian, for example, the category of abelian groups, or the category of vector spaces, or the category of modules over an arbitrary ring, then the sequence is strictly exact if and only if it is exact.
Yeah.
Example 2. Which is our main example. Suppose that A is the category of complete locally convex spaces. Here the situation is different. Our sequence is strictly exact if it satisfies the following conditions. First of all, F is topologically injective. So the first arrow here is this arrow is topologically injective. Second, our sequence should be algebraically exact at Y. So the range of F is the kernel of G. Next, the range of G has to be dense in Z. And finally, G should be an open map onto its range. So it turns out that this combination of properties is equivalent to the strict exactness of our sequence. In other words, this combination of properties means that X can be identified, topologically identified with a subspace in Y, and Z is the completion of the quotient of Y modulo X. And example 3, suppose that A is either the category of Banach spaces or the category of Fréchet spaces. Then it turns out that our sequence is strictly exact in A, even only if it is strictly exact in the category of all complete locally convex spaces. And even only if it is exact in the category of vector spaces. Well, indeed, if it is exact in the category of vector spaces, then the open mapping theorem easily implies that F is topologically injective and G is open. And we have exactness in the middle term. And so our sequence is strictly exact in the category of all complete locally convex spaces. So we have a combination of these properties. And conversely, if our sequence is strictly exact in the category of complete locally convex spaces, so Z can be identified with the completion of the quotient of X modulo of Y modulo X, but the quotient is already complete. The quotient of a Fréchet space modulo a closed subspace is complete, and we have vector space exactness. Okay. There is a useful result which simplifies the working with strictly exact sequences of locally convex spaces. This result is due to Palomodov. If we have a short sequence of complete locally convex spaces, then it is strictly exact in this category, in the category of complete locally convex spaces, if and only if for each set S, the following sequence of vector spaces is exact. So we just apply the functor of morphisms. So script L denotes the set of all continuous linear operators to the space little infinity of S. So we get the following sequence. And Palomodov's theorem states that the original sequence is strictly exact, even only for each set S, this sequence of vector spaces is exact. So this result is a reasonable substitute for Johnsonslemma. which fails in the category of all complete locally convex spaces. But this result looks similar because instead of taking the dual spaces, that is the spaces of continuous linear operators to the complex numbers, we take continuous linear operators to little L infinity of S. Okay. Now we're ready to define flat topological modules. So suppose that we have an admissible subcategory in the category of complete locally convex spaces. And let A be a topological algebra whose underlying vector space is an object of C. And we give the following definition. We say that a left topological A module F is flat if the projective tensor product functor takes admissible sequences of right topological modules to strictly exact sequences of complete locally convex spaces. Well, so if we now compare this definition with the definition of vectorial flatness, so let me show you this suitable picture. So let's look at this sequence. So if F is flat in the sense of our definition, then we don't require the surjectivity of this arrow. So this arrow should be the co-kernel of this one in the category of complete locally convex spaces. But we don't require the subjectivity of this arrow. And this is essential. But on the other hand, we require the topological injectivity of this one and the algebraic exactness here. And similarly, we can define amenable algebras. We say that our algebra A is amenable if its unitization A plus is flat in the respective category of bimodules. And by using this definition, it's quite easy to show that if A is amenable in this sense, then each left module in the respective category is flat. It turns out that this definition of flatness and this definition of amenability, first of all, it is compatible to the respective notions for Banach modules or Banach algebras. Namely, we have the following result. If A is a Banach algebra and X is a flat Banach A module, which is flat in the category of Banach modules, then it is flat as a topological module. Well, this is not entirely obvious because at the first glance, it is harder for X to be flat in the bigger category of all topological modules. But nevertheless, it turns out that these two properties of flatness are equivalent. And by the way, if we well, I don't know if it is true for the vectorial flatness. And as a corollary, we see that if A is an amenable Banach algebra, then A is amenable as a topological algebra. So if now come back to our example, so let me show you the statement. So we have proved that there exists a topological module over C0 of omega, which is not vectorially flat. But well, we know that C0 of omega is an amenable Banach algebra. So now, if we now apply this corollary, we see that C0 of omega is amenable as a topological algebra. And so all topological modules over C0 of omega are flat. And so combining these facts, we conclude that a flat module is not necessarily vectorially flat. And by the way, I don't know about the opposite implication.
Yes.
I conjecture that this is not true, and there are some examples. There should be some examples of vectorially flat modules which are not flat. But at this point, I don't have a concrete example. Okay, now, well, I have 5 minutes left. Oh, 15 minutes left. Okay.
It's according to your wishes.
Well, 15 minutes will be okay, I hope. Let's now look how this definition of flatness and this definition of amenability, how they work in concrete situations. So let's make a short digression into the theory of topological vector spaces. And let's recall the definition of CBDF spaces. Well, suppose that we have a locally convex space E and a subset B of E. By definition, B is a barrel if it is closed. First of all, it is closed. Second, it is absolutely convex, which means that it is convex and it is stable under multiplication by complex numbers of modules less than or equal to 1. And third, it should be absorbing, which means that we have the following equality. Each vector belongs to lambda b for if lambda is big enough. A typical example of a barrel is the closed unit ball in any normed space. And by definition, our space E is barreled if each barrel in E is a neighborhood of 0. Here I follow the standard convention, which is standard for the theory of topological vector spaces, that by a neighborhood of a point, we mean a set which is not necessarily open, but which contains an open neighborhood of the point. So this means that each barrel in E contains an open neighborhood of 0.
Yeah.
It is well known that, so it's a well-known fact that each Fréchet space is barreled. And also it is known that the direct limit of any family of any direct system of barrel spaces is also barreled. So the category of barrel spaces is rather big. I will now give the following definition. We say that E is a BDF space if it satisfies the following conditions. First of all, it is barreled. And second, it has a fundamental sequence of bounded sets, say Bn, a fundamental sequence of bounded sets. Fundamental means that for each bounded subset B in E, each bounded subset is actually contained in one of the sets Bn. Clearly, a Banach space has this property. You can just take closed balls of radius n. Actually, there is a more general notion of a DF space due to Grothendieck. In the definition of a DF space, the first property here, the barreledness condition, should be replaced by some technical weaker condition, which I'm not going to define because I'm interested only in barreled DF spaces. So BDF means just barreled DF space. And DF hints that dual to Fréchet, that is, Grothendieck observed that that strong duals of Fréchet spaces have some interesting property, and then he axiomatized this property and it introduced DF spaces. But at the same time, the class of all DF spaces is bigger than the class of strong duals of Fréchet spaces. Well, here are some examples of BDF spaces. First of all Banach spaces are definitely BDF spaces. And more generally, the direct limit of a sequence of Banach spaces is a BDF space. Also, strong duals of many Fréchet spaces are BDF spaces. Of many, but not all of them. In fact, the truth is that the strong dual of any Fréchet space is a DF space, but it is not necessarily barreled. But for many Fréchet spaces, the strong dual is a BDF space. So we see that there are many natural examples, but on the other hand, let me remark that a Fréchet space can be a BDF space only if it is Banach space. And now we define CBDF spaces to be complete BDF spaces. Okay, let's now come back to flatness and amenability. So suppose that C is either the category of Fréchet spaces or the category of CBDF spaces. And suppose that A is a topological algebra whose underlying topological vector space belongs to C. Then we have the following result, which was originally proved by myself for Fréchet spaces. And then transferred to CBDF spaces in our joint paper with Krzysztof Piszczek. The following two conditions are equivalent. Condition 1, the unitization of our algebra is flat in the respective category of bimodules. Which means that A is amenable in the sense of our definition. And the second property is that A is amenable in the spirit of Johnson. That is, for each topological bimodule in our category, all continuous derivations
are in there.
Yeah, all continuous derivations from A to the dual bimodule X star are inner. Well, at this point, I have to stress that the dual bimodule is not a topological bimodule in our sense. I have already said that in general, the action of A on X star is not jointly continuous. But nevertheless, it is always separately continuous. So formally, we can consider continuous derivations from A to X star. And some of them are inner and some of them are not. So if all of them are inner, then this property turns out to be equivalent to the amenability of A. And the key lemma for the proof of this theorem looks as follows. A left topological module in the respective category, F, is flat if and only if for each left module, for each right module F in the respective category, the X1 space from X to F star vanishes. So again, here F star is not a left topological module. It is in some sense a semi-topological module in the sense that the action is separately continuous. Nevertheless, we can define the derived functor X in exactly the same way. And this property looks like an injectivity type condition on F star. So this lemma is a substitute for the duality between flat and injective Banach modules. So we cannot say that F star is injective for two reasons. First of all, it is not a topological module. And second, even if we extend injectivity to such semi-topological modules, then it will not be injective because X, the first argument, runs over the category of topological modules. But nevertheless, this looks like an injectivity type condition. Yeah. And the proof of this lemma is essentially based on Palamonov's theorem, which I've formulated before. Okay, so my original plan was also to state some other results, our joint results with Krzysztof Piszczek, which give us amenability criterion and amenability criterion for so-called Köthe co-echelon algebras. Unfortunately, I have only 2 minutes left, so maybe I'll just say just a few words without giving explicit definitions.
It's up to you.
I'll try to be very quick.
Co-echelon.
Co-echelon algebras. So what is this? We consider a set V, the so-called weighted set, which consists of countably many sequences, countably many positive sequences, such that Vn plus 1 is less than or equal to Vn. And we consider, well, let's consider, for example, K infinity of V. This is the space of those complex sequences Xn, such that the following supremum, X, well, let's better write Xi, such that the following supremum is finite for some n. In other words, this is the direct limit of the weighted L infinity spaces. And similarly, we can define Kp of V, where P is between 1 and infinity. So they are locally convex spaces, and actually they are BDF spaces, CBDF spaces. And sometimes they are topological algebras under pointwise multiplication. Such algebras were originally studied by Bonnet and Domansky in 2003. I'll not write down the explicit condition, but sometimes, often they are topological algebras. And we call them co-echelon algebras. And one of the results that we obtained by Krzysztof is the following amenability criterion. K infinity of V is amenable, even only if this set V, the weighted set V, is bounded, in the sense that for some n, the sequence Vn is bounded. And since Vn plus 1 is less than or equal to Vn, this means that they are bounded for if n is big enough. Well, this means, this is equivalent to say that there exists n such that Vm is bounded whenever m is greater than or equal to n. Well, we can apply this to some concrete examples of co-echelon algebras. But unfortunately, I have no time to give you some concrete examples. In particular, many, well, not many, but some algebras of germs of holomorphic functions turn out to be amenable when we equip them with the so-called Adamar multiplication. So the Adamar multiplication of the Adamar product of two holomorphic functions is a function which is obtained by taking pointwise product of their Taylor coefficients. So at the first glance, this is a rather strange multiplication on the space of holomorphic functions, but it has some application in operator theory. This is the so-called Adamar multiplication. So, for example, it turns out that the algebra of germs of holomorphic functions at a point on the complex plane is amenable with respect to the Adamar multiplication. Okay, thank you. So I stop here.
Oh, thank you very much. So questions? Anar?
Yeah, I have a question. Well, you know the Taylor's result about exactness, stability under small perturbations of morphisms. Well, if you replace, as far as I know, that's not true for sequences of local kernel spaces. Well, is it true if we replace them with strictly exactness, something like that? So having a strict exact sequence and get a small perturbations of the morphisms, then it still will be exact, strictly exact. Do we have something like that?
Well, I don't know. It seems to be a very important question because of this property of stability naturally appears in spectral theory. Well, but I don't know. I don't know.
Yeah, it seems
That's interesting.
the problem for duality is solved by Palamotov's result, right? So the similar problem maybe is going to work there as well, but I don't know.
Yeah, thank you. That's an interesting question.
Okay.
Interesting to think about it.
Yeah. Good question. Other questions? Okay. I remember this. It is this paper of Palomodov in Uspekhi, yes?
Yeah.
This,
homological methods in the theory of logical vector spaces.
Very influential at that time it was. Okay. So now our academic year is over. Thank you. First of all, our speakers, and all people who had an interest and used to hear us. Very pleasant, and let's hope that we shall be alive and vigorous, and we shall meet each other next academic year. So thank you, and I wish everybody a good summer, and whatever in such situation as we know can be suggested to people. Okay, thanks a lot.
Thank you.
Thank you.
Thanks.